Thank you very much. Thank you everyone for coming. I would normally at this point read from the website the description and bio of Jolanda Becker, who is giving this talk. There isn't one. So all I'm going to say is thank you, Jolanda. Make you look. I'm not going to read that long title because you're about to read it to us. Jolanda, please.
I think everyone can hear me now. That should be fine. Okay, yeah, welcome and thanks for sitting through the little eyes that are sitting and making you nervous. So yeah, excited to share this talk with you. It is an exciting topic and I'm glad we're having a good turnout. I think this is the biggest live audience I've done a presentation for. So yeah, I'm excited. What I'm going to be talking to you about today is the use of Siamese neural networks for building change detections at the City of Cape Town. And so I'm going to explain exactly what that means. First, I didn't submit a bio, but I was planning to do one as part of my presentation. So I am actually a mechanical engineer. I have 10 years of experience, more operational experience as a field service engineer at everyone's favorite electricity utility. So Gordon likes to say that the load shedding got increasingly worse by the time I left in 2022, beginning of 2022. So I then, while I was still there, I did a master's in industrial engineering. It was a research master's more on quality management. If anyone is pursuing an ISO 9001 certification, you can also come and speak to me. I then sort of lost interest in that a bit, to be honest, and then really started developing an interest in data. So I then embarked on another master's with a focus on data science and in industrial engineering again. And while I was busy with that, I got the opportunity to join the city at the beginning of 2022. Started out as a data analyst, and in mid-2023, I moved over to the data scientist role. And so next, I just want to talk a bit about our organization and our department within this organization. So so you all will be familiar with the City of Cape Town and might be surprised to hear that the City of Cape Town has a data science department. We're about 12 people. And we are a growing team. So we appoint, I think there's 3 new people that started in July. So we operate more or less like internal consultants to the city. And we work across virtually all of the different directorates like energy, water and sanitation, safety and security, spatial planning, to do different projects. And what we are aiming to do is drive the adoption of advanced analytic methods within existing processes to drive operational efficiency, continuous improvement, that kind of thing. And so what I'm going to be talking to you about today is in the spatial planning / sort of finance revenue collection space within our organization. Okay, so first of all, I'm going to talk a bit about what is our organization's need in terms of the current process that we have. So one of the things that the city needs to do, among myriad of other things, is to maintain an up-to-date cadastral data set. And so what this is, it's basically just all of the information that pertains to all of the properties and the boundaries between properties within the city. And together with this, we need to, the city needs to maintain an accurate valuations role. So there is an existing process to monitor value-altering changes to properties, to building on properties within the City of Cape Town. And this is industrial, commercial, and residential properties. And so if this process has the ability to trigger supplementary valuations if there is a change picked up, which then usually either results in an in-person inspection or a desktop inspection. And if they find that there is a value-altering change, then the valuation role gets updated. So that's the need of the organization. So I'll go through what the existing process looks like now. So the city uses something called digital surface modeling. And so this is data that's collected using a small aircraft that flies the whole area of the city and collects LiDAR data, and then builds height maps that look something like those images. And if the difference in height is above a certain threshold, then that sort of becomes a flag and then gets reviewed by a person. And if it is found that the visual inspection shows a change to the building, then that triggers that supplementary valuation that we talked about. So this process is quite sensitive. It generates about 600,000 flags. It's a lot. The city has about 850,000 residential properties, to just give you an idea of the scale. And so this sort of gets consolidated through some GIS methods into flagging 60,000 properties that have potential changes on them. Then there's literally people that are appointed to just look at images between different years, sort of toggle between them and see if there is a change on the property. And after that, the 60,000 properties there's actually 6,000 property changes. So it's about a 10% conversion rate. So, yeah. So there's obviously some limitations or things that are not ideal about this process. So there's a very, very high level of human review required for this process. It's tiresome and tedious work. You can imagine doing this the whole day. Not nice work to do. There's the high false positive rate, so about 90% of the properties end up being false positives. And it's costly to obtain the DSM data as well. So in this project and with our involvement, the aim was to investigate whether advanced analytic methods cannot be pulled in to address some of these limitations. And especially considering the human visual review aspect, I think the question that we asked is, can a computer actually do this instead of a human? So next, I want to talk a bit about deep learning potential in terms of developing a solution for this. We did consider some more conventional machine learning methods as well. I'm not going to go into that today just because of time. But yeah, in the end, deep learning was the one we went with, and I'll explain why we did that. So deep learning is something that's very well suited to complex problems. And we can think about our problem as being complex in a couple of different ways. So if you think about an image that looks something like the small block up there, if you zoom into like a little part of it, it'll look something like this, and there'll be values associated with each block. Now, what this translates to in a data format is basically if you have 100 by 100, let me rather say this, each block becomes a column in a data set. So if you have 100 by 100 image, which is very small, considered very small, you'll have 10,000 features, which means in your data set, you'll have 10,000 columns. So it's complex in terms of the scale of the number of features that you need to deal with. Whereas if you think of something more conventional machine learning type of problems, it'll be maybe in the order of 15, 20, maybe 50 at most columns in your data set. Then also, it's also complex in that the change that you're looking for is not always going to show up in the same, let me just get my mouse here, in the same pixels. For one property, it might be here. For another property, it might be there. So conventional machine learning is well geared to look for patterns that will typically show up in the same columns or different combinations. Whereas here, you don't have that. Your data is not going to show that. So to be able to deal with that complexity, deep learning is actually quite well suited. And if you think about something like a cat versus a dog classifier, if you're feeding it data, then both cats and dogs have noses, but it needs to learn the intricacies of what the difference is, and that nose is going to be in a slightly different spot every time. So that's the type of complexity that deep learning is good with dealing with. So our problem is well suited to computer vision. So I just want to talk about the data sources that we have. So maybe just of a plug, this is one of the great things about working for the city. We have lots of data, which is amazing. We have really interesting problems. So yeah, come and speak to us. So what we had is we didn't have like sort of polygons drawn around changes, but we did have like this property does have a change. So we basically had like a sort of a binary labels, 1 for change and 0 for non-change. So we had label data, we could do supervised learning. And also the city does have, because it's been doing this DSM data collection for quite a number of years, it has a lot of aerial imagery, high resolution aerial imagery of the city, which we could use for our training. So yeah, we had two really great data sources. Okay, so now I'm just going to talk a bit about neural networks, because that's the model type that you use for deep learning. And so I just like to do I have a little analogy that I sort of use to explain it very simply, and it's very simplified. There's this video link. It's by, I think it's 1 Brown 3 Blue. It's a really good video on how neural networks work. It's very interesting. But the analogy that I use is, maybe I must first just explain. This is typically what a neural network looks like. This is the input layer. And so each one of your columns in your data set will be a node. And then you have the network. Each one of these nodes and each one of the arrows has a value. And then your output layer is whatever your prediction is going to be. We have a binary prediction, so it's just going to be one node. So each one of these paths, you can see it really becomes, it's an absolute exponential multiplier. So each one of these paths basically makes an equation. So that looks something like this. Now, if you think back, and this is the analogy back to like sort of high school maths, if you have 2 variables and 2 equations, then you can solve for both variables. And so what happens with deep learning is you basically have millions of variables and millions of equations. Computers are really good at doing like a lot of tasks very fast, so computers are able to solve these things. Something that's a bit more complicated is that it's very hard to get the exact correct answer, but if we can get an approximate answer, that might be good enough. To get the exact answer can take very long in terms of training. But then you decide sort of your application, what's going to be an acceptable level of accuracy. And so the sort of like hello world examples of neural network classifiers is the MNIST numbers, handwritten numbers. So here's an example of that there. And just the cat versus dog classifier. So you feed it a lot of images of cats and dogs. It learns what the ideal network is going to be able to classify between the two. It gives you prediction, cats or dogs. That's sort of how it works. So our problem that we are dealing with is now not a straightforward classifier. We actually want to evaluate 2 images. So we want to see, this is the image now, this is the image a year later, is there a change? So we can't use this architecture. We need to use basically an architecture that can accommodate 2 images and the task that we want to do. So we did some research. What we found is you get something called a Siamese neural network. And so where this is often used is things like facial recognition. And so how it works simply is that if you have 2 images, you'll see those ones at the top it's a bit small, but it's of the same person. So you train your neural network. So this is the neural network. This is actually the same network. You feed this image to this network. If it's trained, I'm going to give an example what it does when it's trained. You give this image to the network. For each image, it's going to spit out a vector of about like 50 different values. And you know, like if you think back to physics, school physics, if you have a vector, then you can plot it usually as locations. And so what it does for images that are the same, it plots them close together. For images that are not the same, it plots them far from one another. And then your cost function takes that into account and then learns to be able to identify they're close to one another, they're the same, they're far from one another, it's not the same. So that's sort of also simplified how Siamese neural networks work. And so, yeah, next we're going to go on a bit of an adventure in model development. Yeah. With these kinds of things, you have to, there's a lot of potential for it to work, but you don't know if it's going to work. So you have to try a lot of things and just see what happens. So what we started off with sort of as just to see if it will work is actually using Sentinel-2 low resolution data. And I have a representation of more or less what that looks like. So it's very low resolution because we're cropping basically to a property outline, and often a property might only be like 1 pixel in certain of the layers. And so this is what it looks like. It ended up that inherently the data, it just doesn't have enough information for the model to learn to be able to do the distinguishing. So so we tried that, we canned that, it didn't work. Next, we pivoted back to aerial imagery. So much higher resolution, a lot of information. And so it did end up, we'll get to it, inherently, or maybe a way to think about it, if a human can see that there's a change, there's a good chance that a model will also be able to see that there is a change. So in training our model with the aerial imagery, we did reduce the resolution basically tenfold. So it started out, this is the full resolution of a property, and this is actually reduced tenfold. So you can see there's still more than enough information here for the model to learn from. And something that also happened, that's sort of a happy accident, we did have it in mind, but it ended up working out quite nicely, is that by us reducing the resolution so much, it ended up being a bit more coarse, the aerial imagery, reduced resolution, being a bit more coarse than high-resolution satellite imagery, which means that theoretically, our model that's trained on aerial imagery will be able to work on high-resolution satellite imagery, which could be a lot cheaper to acquire than the aerial imagery. Okay, so we first did an initial model. So we basically fed it images that's this, this shape at lower resolution. So you can see that there is some of the neighbors' properties is also in here. And the model ended up, we got good enough accuracies. But what we did find is, because the model is so good at learning the complexities, it ended up picking up changes on the neighboring properties as well. So it'll flag an image to say that there is a property, but then it'll be here, for instance. So, which is not ideal for our the people, the data, processes, the existing process. They want to know that it's only going to be on this property, it's not going to be on the neighbors. It doesn't work for the business process to have it like that. So we pivoted again after that. So it's a long range of just pivoting to try different things, and that's the just the nature of model development, is to basically have the images look more something like this, where we mask out the neighbors. So the model is only seeing information about that specific property. And so there's another example of what that looked like. And we did that as mitigation for picking up neighboring changes. And doing this, we achieved comparable metrics than we did with the one with the non-masked model. And so this is sort of, after all of that, the very quick, it's just a change in a slide, but for us it was like a lot of work and tinkering. but this is sort of the eventual performance that we saw. So we're getting about a 66 accuracy, 66% accuracy. And our sensitivity and specificity is at 68% and 66%. And you can sort of see the confusion matrix there in terms of you want to see big numbers here. You're obviously seeing smaller numbers here because there's a lot less changes than there are non-changes. So that's why you're seeing that. But you want to sort of see that all of these scores are good. So what does this mean? So we stared a lot at those confusion matrices. We confused ourselves thoroughly, also looking at them. So yeah, in terms of just a reminder of sort of the stats of the existing process, it's 600,000 flags, which then gets consolidated to 60,000 properties being flagged, and 6,000 of them end up being actual changes. So if we consider bringing in the model and applying it basically to the 60,000 properties that were flagged, then we see that we're actually going to reduce that amount of properties to about 19,000. So it'll be a reduction in 40,000 images that the staff will need to review physically. And of that 19,000, about 4,000 will be actual changes. So we're losing some accuracy or some changes, but we're reducing the number of images that the staff need to review drastically. And so this is good enough to actually supplement the 60,000 step. Which is great. So we're going ahead in terms of seeing how we can incorporate this in the existing process. If we consider one up, the 600,000 flags, or the correct way to think about it is to think about this about 850,000 residential properties. So or that 800,000, if we apply the model to 800,000 properties without the DSM step, then we'll flag about 250,000 properties. That's way too much for people to review, and we'll still only get about 4,080 changes. So there's more work that needs further development that we need to do, but there's already big potential in order to apply it at the 60,000 level. So in terms of future work, what we figured out we need to do is actually train, where's my mouse, for specificity instead of sensitivity. So this is confusing. We basically want this value to be very high and this to be very low. So basically prioritize specificity, that value, and try to get that as good as possible. And there's different ways to try and do that. So there's a setting that you can set for it to do that. So you say we aim for 90% or 95% here, and let's see how good we can get that one. So that's something that we're doing at the moment. There's other sort of architectures or training generation options. So what you do is you actually give the model 3 images. So you'll give it an anchor and a positive. So that'll be, for instance, a property in 2018 with no change, a property in 2019 with no change, and a property in 2020 with a change. And then you train the neural network, and then you extract it from that training architecture and you put it back into your Siamese neural network. Excuse me. It can only take 2 images, and then you can also, it learns the correct, you have a different cost function as well called the triplet loss function. It learns to be able to do that distinguishing. That's also something that we're busy with at the moment. Then we're also looking at metadata enriching. We have a lot of billing data as a city. You'll receive your bills if you're staying in Cape Town. So we have all of that data. And then just in general, trying things, being creative. There's a lot of that. So yeah, there's a lot that we still can do. And yeah, we're very encouraged with the results that we're getting at the moment. And yeah, there we go.
Fantastic. Thank you, Jolanda. I was going to ask if there's questions. I see there's already hands, so I'm going to take the advantage because I've got the microphone to ask a question first. The masking that you did to reduce basically the square image to the one with the funny shape, is
Yeah.
that just from cadastral data? As in, you've got coordinates of what people's properties' borderlines look like?
Yes,
Okay.
we have that,
Cool.
yeah.
I was really only saying that because it shows off that I know what cadastral means. And I only know that because I had to look it up a couple of months ago for work. Before that was a word I'd never heard before. It means property borders, if you're wondering.
Yeah.
Well, not quite, but close. Okay, question over there.
Thank you. That was a lovely talk. Fascinating. You mentioned that you have a 10,000 column data set. Postgres column limit is 1,600 columns. So I'm curious to know what database you used.
So, might ask my colleague to come in here, but so I'm just loading it into my local machine and then using that. So I'm not using something like Postgres. I'm just doing it in my image. So yeah. Yeah. Yeah, I'll mention that as well.
I enjoyed that. Thank you very much.
Okay.
I was going to say more comment than a question. I probably shouldn't now. But one related to the false positive rate of the images. I don't want to say Cape Town and UCT famously has a budding radar community. Any particular reason for the false positives? You don't have to answer that. And then two, on the reduced resolution of the imagery that you used and led to your happy accident. Any particular reason for going with the reduced? Was it sort of to prioritize the throughput of learning, or was it just because you got fed up with processing higher res imagery?
So what happened is it literally the model training would fall over if I did the high resolution. But we have, I didn't actually speak a lot about that. We did have in mind to at some point go into the high resolution satellite imagery. So it was also, that is something that we did think about. So yeah, that's how it sort of worked out.
Hi, thanks. It's nice to see a real application, not just an academic exercise. My question is, how much, I have two questions. The first one is, how much data normalization did you have to do? Because I mean, you can imagine an image from a year ago on a sunny day is not going to look the same as an image today on a cloudy day. And also shadows in the afternoon are not going to look like shadows in the morning. So how much data normalization did you have to do, and what kind of things did you do? And then my second question is, you obviously have very imbalanced data.
Yes.
So what techniques did you use to actually address that?
Okay, two excellent questions. Definitely the stuff we needed to think about. So in terms of the normalization, we applied actually no normalization. But what we did do is we would draw images from different years. And then the idea is that the model actually learns to be able to deal with those kind of differences in shadows and sunniness. And yeah, so we didn't do it. To answer that question, we actually didn't do any normalization. I think if you doing maybe more conventional machine learning, that is required, and applying something like indexes in NDVI, stuff like that, can be beneficial. But because we were dealing with deep learning, it wasn't necessary. In terms of the imbalanced classes, I think that's also why we're running into that sensitivity specificity issue. What you need to do with deep learning is you need to train with balanced classes, because if you're training with imbalanced classes, so what I mean with that, if you basically taking the 6,000 images that have changes and 800,000 that doesn't, and you sort of do it in that ratio, your model is just going to learn to always predict no change, because it's seeing it's correct 98% of the time. So you have to train with balanced classes. And then afterwards, you need to very carefully think about your confusion matrices in terms of and doing your accuracies actually at the end on your testing set. You can actually have that ratio in your testing set and check that the accuracy is as you expect it to be. And then also that option of training for specificity or sensitivity at a certain specificity. That's also a way to deal with the imbalanced classes.
Can you talk a bit about how you're approaching retraining of the models? I'm assuming that through the process of validating the outputs of these, you're capturing those and hopefully feeding those back into your system.
Yes. So we are still in sort of the initial training phase, but that's definitely something that you need to think about. You need to monitor, if you're going to productionalize or put it in a process, you need to monitor your outputs to make sure that the accuracy is still as you expect it to be. And then it is always good to feed that back. So basically how that works if you're programming it is you literally take your you load your model with all of the correct architecture and you create a new data set, and then you do further training. You keep some of the data aside for testing afterwards, and then you check that the accuracies is what you expect it to be. Probably at once you do a lot of tuning, you might change some of the stuff. But then there's also an option, you can retrain a model, like completely from scratch. You can, so there's two options. You can retrain it. The training isn't so expensive that you cannot retrain it completely from scratch on updated data. But there is also the option to take the model and further train it. Neither one of them is a very expensive process, so you can do both.
Okay. Yes, hi, Yolanda. Yes, small comment. So I'm from the city. We have a stand. Unfortunately, we don't have any swag, but we do have hope for all. And if you'd like to see some of our demos, you can pop around there. I won't be there lunchtime, so the demo's on you guys. But there is a demo of this tool and some of our other data science tools. I think there's a voice to text where we're kind of taking service requests and taking voice to text, and we have an API for that and some stuff that we'll probably see later on today. Cool.
There's a demo, he says. I won't be there, he says. You get the number of that bus, that city bus that vroom through his colleagues. Yeah. Question over there.
One comment, one question. The comment was just linking this to another talk yesterday on diffusion. I was thinking that you could maybe make use of diffusion to enhance the resolution of the satellite imagery, and that could maybe get you some good gains. The question I had was, did you look at multispectral indices? So I know that on an image it's red, green, blue, right? Those are the three layers.
Yeah.
But if you use the sentinel imagery, you get, I think it's 13 layers. So you can you could look at near infrared and that kind of stuff too.
Yes.
Did you kind of look at any of that?
So on our adventures with the low resolution, we really tried to get that to work. We did consider all the different indexes, doing combination of indexes, doing stuff like metrics like NDVI. We didn't have much success with that. It didn't improve, but I mean that's more. I think it's more related to it's being too low res. It's something to try. In the aerial imagery, we obviously don't have that available. If we do get the satellite imagery, high res, that is something that we could definitely try. Like I said, this in terms of try anything. Almost anything is worth trying. So yeah.
Hey, okay. It's a very simple question. It's mostly focusing on the collection of the data. Do you guys take in consideration the township as well?
Yes, so that's another really good question. So the data that we provide the model during training is sampled across the whole of the city. So so all types of properties. And so the current model is able to deal with the complexities of, for instance, a house in Durbanville versus a house in Gugulethu, because it's seen that kind of data in its training data. It's not something we're doing explicitly, it's sort of implicit in terms of the data that we do provide. So it is able to deal with that, yeah.
Really good work. Just a question, apart from, you called it the cadastral information, did you use other techniques to align the two images, or just that information?
Just that information. So we didn't need to do much aligning because we're cropping to we know what the outlines is and the extremes. Can't remember what you call it. So we just took for instance, the image from 2018, doing it in a bit of a different way, but simplified. We're taking the big image from 2018, cropping it to exactly the outlines of the property, and then taking the image from 2019, cropping it exactly to the outline, and then making sure that the resolution is the same. So yeah, that's how we did it.
Brilliant. I think I haven't had this many questions, or I haven't passed the microphones around much all of yesterday, so fantastic. Are there more questions? Anybody got any others? Hands are there.
Do you have access to Sentinel-3 data?
No. Simple. Simple answer. I think there was another question down there.
That's my steps for the day. So, just have to pass that along.
Hi, okay. So a few years back, SANS actually released a data set where they kind of did the same thing but on informed settlement growth, and then they did it over the whole SA with satellite data. So I was just wondering, did you take that as an inspiration? Did you work with that? Did you copy that? Any partnership or anything you learned from that? Just more or less.
Yeah. So I did. I'm not aware of that. So I think the inspiration sort of came with the data that we have available and the business need. But something that we did do earlier this year that's still quite exploratory in nature is trying to estimate the number of informality in an area. And so, because the city can use that for planning, and it's specific, or rather not informality, it's the level of backyarding. So people will have houses and then they'll have smaller, more informal structures at the back of their property that they rent out. And you want to know that obviously increases the amount of people that stay in an area more than what the physical building plans will tell you is living there. And so what we did there is Google does basically of the whole world analysis of the buildings and outlines, and it gives you it actually gives you the polygons, but it also gives you a confidence level of how confident it is of that structure. And so the hypothesis was that if it's a low level of confidence, then it might be a more informal structure. So so what we did is we looked at areas and sort of the average confidence level of the buildings that was picked up through that process. And that ended up being a very good informality predictor. So you could see that the areas that were informal, there was a lower average confidence. And the more formal areas, there was higher confidence. And so we're still looking exactly how we can use that. But so it is something that the city is thinking about and needs to know about for planning purposes as well.
Thank you for the talk. I'm actually curious, what was the most challenging task throughout this process from like the data collection and the modeling?
Okay, that's also a good question. I didn't get to in my presentation. So something that's very time-consuming is actually the data preparation, because you can think of what we're doing in a simple format is taking a super big image of the whole city at high resolution and then cropping it to little images of the properties. And so I initially did the data prep, where I was basically not exactly doing, I was doing a WMS call to get the image and then cropping it. And if I needed to prep the 800,000 properties in the city with my process, it basically took 2 weeks to do that, so that's quite a long time. Then I got my colleague, Gordon, which you would have seen yesterday in the lightning talks, got him involved, and it's just a testament to different people who are good at different things. And so he has more of a data engineering, computer engineering background, and I don't know, he must explain exactly how he did that, but he brought it down to 2 days. So yeah, so it was challenging for me initially to do that because it's just like waiting for it to happen. You're like keen to start training your model and to do all of that exactly so that it's going to be uniform across your data set. So I sort of figured out the method and Gordon like sped it up a lot. So yeah.
So it's a bit of a weird question. I'm going to try to formulate it. So let's say you take some data from like day one and today, I don't know, a week later, and you notice some changes. That's great. But you said in your talk that this new method, you only pick up about 4,000 of the 6,000 changes. So there's definitely stuff that gets missed. So now if you take another picture a week later, maybe you miss something in those first 2 weeks. So do you like, how do you keep track of like individual properties? Do you say like, do you maintain multiple timestamps for properties? So like, oh, last time we actually saw a change on this was at this date. So we only need to compare stuff to this date. Or do you look at historical data as well?
Yeah. Also a great question. So what we would do is we would check for day 1 and day 2, and then next we'll check for day 2 and day 3. But a weakness in the process is if you miss the change, and we know we're going to miss changes between day 1 and 2, the change is going to already have taken place here. So you're going to miss it. You're going to miss it from day 2 to 3. So yeah.
Thank you. I think we've got pretty much time for one more question. Does anybody have one to put? Or of course.
Sure. Okay. So thanks for that, Jolanda. I think this is now the 5th time I've heard this, but it was definitely one of the better ones. I suppose, something that I think is really interesting is you're coming from, an operational engineering background. You've, come into data science and data analytics, and this is probably the first big project where you've been applying data science in a very operational setting. Do you mind just reflecting a little bit about how that experience has been relative to what you studied, and then also maybe even thinking about how you would have approached things in the before times when you were an operational engineer?
So something I do always think about, and that I credit sort of my my operational experience for, is it's very important to think how the model or whatever it is that you're doing is going to be used. How is it actually going to benefit the operational people that need to use it in the end? And I think a lot of people sort of fall in the trap of thinking about that at the end, and then it's sort of often you've missed something, and then it's hard to go back, or you need to almost sometimes start from scratch. So it's really good to have sort of that way of thinking at the start and shaping what it is that you are developing in terms of how it is going to be used. So I think, that is always something I endeavor to do, and that I think is sort of a strength in terms of the experience that I have. Trying to think of, am I answering Gordon's question now? I think when I was doing things more when I was still very operational. I couldn't program. Basically, Excel was almost my best tool that I have, and that already then felt frustrating because you're limited in what you can do. So when I did get the skills to be able to program or code and develop models and do a lot more complex thing, I really felt like the weights were shed and I could just run with what I wanted to and needed to do. So yeah.
Perfect. Thank you, Jolanda. I think well done, everyone. We've taken 20 minutes in questions. I mean, that's pretty impressive. So that's testament to your fantastic talk, Jolanda. So thank you very much. That was absolutely brilliant.